Wait, what? I think we're live.
Yeah. Great.
All right, so let's continue this morning session with what's your name? Hlér Kristjánsson, who's going to tell us about resource theories of communication. So please, you have about 20 minutes to tell us about your results, and then I will try to put forward the questions of the audience that you can write in Slack.
Yeah.
There you go.
Okay. Thank you very much for the introduction. So I'm going to talk about resource theories of communication. So this is a joint work with my PhD supervisor, Giulio Chiribella, as well as Sina Salek, Daniel Eble, and Matthew Wilson, who is doing the tech, and you'll also see him later today. So this work is about the paper recently being published in the New Journal of Physics, and you can also find it on the archive on this link. And the aim of this work is to kind of formulate formally a resource theoretic framework to capture the new models of communication that have been proposed in the last couple of years, such as with indefinite causal order and coherent control of processes, and to quantify the communication advantages associated with those. So I'll start by giving some background and motivations, then explain the new framework that we've made, and then finally apply this to actually the superpositions of causal orders, superpositions of channels, and other paradigms of communication. So let's start with Shannon theory. So that's the kind of traditional theory of communication. So let's start with a classical case. So classically, we have some information carriers, classical information carriers represented by this coin I've drawn here. And the coin, or this classical particle, is sent through a classical communication channel through a well-defined trajectory. Now we can generalize this to the quantum case, where we have quantum Shannon theory, where we now allow quantum particles. So for example, this photon can travel through a quantum transmission line. However, there's a sense in which the transition from classical to quantum is not complete, in the sense that in both of these cases, the configuration of the transmission lines is still classical. And this really asks for a second level of quantization of Shannon theory, where also the configuration of the transmission lines themselves is in a quantum superposition. And this new paradigm has really been the subject of a lot of work in the last couple of years, where we have had works on superpositions of trajectories. So a single particle is sent in a superposition through channel A and channel B. Even more exotically, we can have superpositions of causal orders. So this operation known as the quantum switch, where a particle is sent through A and then B, or B and then A, in a superposition of the two possible classical orderings. Now, these new paradigms of communication have been shown to yield a wide range of communication advantages in comparison to standard quantum Shannon theory, as you can see in this large set of papers here. Similarly, coherently controlling a channel, creating such a coherently controlling two channels to create a superposition of trajectories, has also been shown to yield communication advantages, as you can see in these papers. However, the relation between these different types of advantages and their exact nature has been a subject of some considerable debate in the last couple of years. So, for example, some authors have argued or questioned the extent to which indefinite causal order per se is responsible for the communication advantages for example, associated with the quantum switch in comparison to a coherent control of quantum channels in a definite causal order. I won't go into the details of this debate here, but it suffices to say that it raises two important questions. First of all, how should potential advantages of novel paradigms of communication be quantified and compared? And secondly, what is the origin of the advantages associated with each paradigm? And in this work, we propose an answer to the first question and set the scene for future work on the latter question. We do this by formulating a resource theory of communication, which quantifies the differences between different forms of coherent control of channels, so orders or trajectories, etc., and provides a framework to define any new types of communication, including those that are not related to the discussions we've had in the last couple of years about superpositions of orders, but any paradigm of communication should fit into our resource theory. So, okay, now let's ask, what is a resource theory? Well, in this conference, I'm happy to say that the resource theory is just a symmetric monoidal category where the objects represent some resources and the morphisms represent some free transformations of those resources. So, for example, we can consider the category of 19th century Iceland. So this is what my great-grandparents are doing. So you can see that there are some sheep, and then there is food and some sweaters, and the sheep can be converted to food with a farmer, and the farmer is kind of the morphism here. And similarly, if you have a grandmother, she can also convert the sheep to wool and sweaters. And then you have the snow there, which doesn't do anything. The snow is kind of like the trivial resource. You can read more about resource theories in general in the paper by Bob and co-authors on the bottom of the slide. But in our case, the resource theory is going to be a bit more elaborate. So the resources in our theory of communication are quantum channels, so completely positive trace-preserving maps. Now, the possible transformations of these resources, by definition, are supermaps. So quantum supermaps are defined as the mathematical objects that transform quantum channels to quantum channels. We take our free transformations to be some restricted set of these supermaps. So we pick some choice of supermaps and we take those to be the free transformations of our resources. So let's start now by investigating standard quantum channel theory as the first example. So the theory we all know and love, and see how this fits into the resource theoretical framework before extending to novel extensions of this. So in our resource theory, the channels are split into two types. Firstly, we have what we call unplaced channels. So these are just kind of arbitrary mathematical quantum channels. So quantum channels with some arbitrary input and output systems, say x1, y1, corresponding to some quantum system of a fixed dimension. But importantly, they have no interpretation of being placed anywhere between any agents or communicating parties. They're just mathematical quantum systems, hence the name unplaced. Secondly, we have what we call placed channels. So you can imagine that these channels are really placed between two communicating parties. So the input of a placed channel is placed at the space-time location of some sender, and the output as some receiver. For example, here on the left, you have the input placed at Alice and the output at Ray. Our first free transformation is going to be the basic placement supermap, which we can interpret as some operation performed by a communication provider. So before the communicating parties have access to these channels. So what is this? Well, these are maps that take unplaced channels and simply place them between the communicating parties in really the simplest possible way. So the basic placement supermap takes an unplaced channel, takes the input of that channel and maps it to an isomorphic input that is really of the same dimension as the original one. So we take X and map it to A, where A is isomorphic to X, but just has this additional interpretation of being localized at the space-time point corresponding to some communicating party, in this case, the sender Alice. Similarly, we have the isomorphism W for the output, so Y is placed at Bob's end. And overall, this whole placed channel, so the channel that consists of the unplaced channel, together with these isomorphisms between unplaced and placed system types, we call that the placed channel, denoted C, which is a place channel between Alice and Bob. Okay, so now with the basic placement supermap, we can similarly define a parallel placement. So this is really just a simple generalization. You take two channels, tensor product of two different placements, and you place two channels between the same two communicating parties. A little bit more elaborate is the sequential placement. So in this case, if we have three communicating parties, Alice, the sender, Ray, the repeater, and Bob, the receiver, we can also take a tensor product of two placement supermaps. But this time, the placement supermaps correspond to different input and output systems. So we can place the first channel between Alice and Ray and the second channel between Ray and Bob. And the output of this placement supermap is no longer an ordinary quantum channel, but it's now a quantum comb. So a quantum comb with one open slot, as you can see in this picture here. Okay. Now, in principle, this can be generalized to any directed acyclic graph or any network of communicating parties in a fixed causal order. So you can just take tensor products of these placement supermaps and place the channels in any way that respects the causal order of the communicating parties. But after the communication provider has placed the channels, we allow a second type of supermap. And these we call party supermaps. And party supermaps are just the supermaps that are interpreted as being performed by the communicating parties themselves. In this case, Alice, Ray, and Bob. And the three party supermap that we take in our standard quantum Shannon theory are those of the form of encoding, repeater, and decoding. So that these three supermaps that we take here are just the ones that can be performed by local operations of Alice, Ray, and Bob without any additional ancillary channels. So a general resource theory communication motivated by standard Shannon theory is, as we have said, specified by a set of three supermaps M3 containing A, placement supermaps, and B, party supermaps. Now, in principle, any choice of three supermaps defines some resource theory of communication. But that resource theory of communication need not be interesting. So we need to have some additional restriction on the types of allowed supermaps. For example, we can consider this supermap, where for any unplaced channels that the communication parties and providers have access to, this supermap just takes those channels and throws them in the bin, and instead replaces it by placing a perfect optical fiber between Alice and Bob. Now, clearly, if we were to allow such operations as a free operation in our resource theory of communication, then this theory would become trivial, because completely independently of what devices we started with, we can always communicate. So the supermaps no longer capture an idea of using the original communication channels, because there's kind of a side channel that's been generated that really bypasses the original channels. So we propose a minimal requirement for any resource theory of communication that it does not generate side channels. We stress that it's a minimal requirement, so not necessarily all such theories that satisfy it are interesting, but at least it's a baseline that needs to be respected. So mathematically, we say that the resource theory should not contain any supermaps that generate side channels. So mathematically, what is a side channel? Sort of in general, rather than just the example we gave, well, we say that a supermap S generates side channels if there exists another free supermap S prime, such that for any choice of input channels, S prime acting on S, acting on the channels, is equal to some placed fixed channel C, which has non-zero capacity. So this really captures the fact that whatever input channels you started with, you get some fixed channel that can communicate. So in this example, we could take, for example, S prime to just be some fixed encoding and decoding operations by the communicating parties. Well, then if we can always get a fixed channel, then the supermaps really don't depend on the original channels, and we can say that they are really trivial. So now, in the last part of this talk, let's apply this resource theoretic framework to the extensions of standard quantum Shannon theory that have been proposed in recent years, and see how they, maybe try and get some intuition of how they compare and how we should understand the communication advantages. So the first example we're going to take is a superposition of encoding operations. So this was really proposed as a challenge to the quantum switch we briefly mentioned at the beginning. So in the quantum switch, there is some control qubit that coherently controls the order of application of channels. And so you can really ask the question, well, if we can coherently control the order of channels, why can we not simply just take the control qubit and the message and put them together through a C0 gate? And clearly, we know from phase kickback that this can also give communication possibilities, even though the channels that we use are completely noisy. Well, with our resource theoretic framework, the answer to this question arises naturally. This protocol, where we have kind of a superposition of encoding, so a superposition of the identity and the X gate, i.e. the C0, this generates communication independently of what channels you have. So whatever noisy channels you have, it doesn't matter. This protocol can always give you noiseless communication of 1 bit. And therefore, we say that this generates side channels and should not be considered as a valid candidate for a theory of communication. Now, the quantum switch itself can be thought of as a placement supermap. So we start with the unplaced channels, place them in an indefinite configuration between the communicating parties, and out comes a new place channel, S of N1 and N2, between Alice and Bob, with input system A, output system B, and additional order qubit, which determines the order of the channels, which is initialized in the plus state. And we prove in our work that the quantum switch does not generate side channels. We also have the superposition placement. So this is a bit more complicated than the quantum switch, for the simple reason that if I have 2 quantum channels, there does not exist any supermap that coherently controls whether a state is sent through one channel or the other directly. So there's no supermap that does this. It depends only on the original channels themselves. So what we need to do is actually consider an extension to these channels. So we call this the vacuum extension. So we need to consider how this channel acts in the absence of an input. So starting with an original channel, let's say N, we can define a channel N tilde that acts as N when the input is restricted to a state, and as the identity on the vacuum when the input is a vacuum. We call these channels N tilde. And with this in place, we can now define a kind of superposition of 2 channels specified by these vacuum extensions, which are in general non-unique, by the equation you can see at the bottom. So I can have this kind of isomorphism U between a message M and the path P. So the path P is some qubit. Now, if the qubit is in state 0, I send the message, the state, really through the channel on the left and the vacuum on the right, and vice versa if the path is in the state 1. Importantly, this placement supermap that places 2 vacuum-extended channels in a superposition results in a place channel that is itself an ordinary quantum channel between Alice and Bob. So the vacuum only appears in the middle. This is just an ordinary channel where Alice encodes a message, Bob can decode the message, and there is an additional path qubit that is initialized in the plus state, so initialized fixed in the plus state. You can read more about the formalism in the paper of ours cited at the bottom. Now, from this, an important conclusion is that the quantum switch and the superposition placements take different types of initial resources. So the quantum switch takes ordinary quantum channels as resources, whilst the superposition placement takes an extension of the original channels, so these vacuum extended channels, which act coherently on the vacuum sector and the original particle sector. So it's important that any comparison between communication advantages arising from the 2 placement supermaps needs to be very careful. So we need to be very careful when we compare the 2 because they're not acting on the same type of resources. So this leads us to a summary of the talk. So we have presented a resource theory of communication where we have as resources unplaced channels and placed channels between the communicating parties. As free transformations, we have supermaps, placement supermaps on the one hand that place unplaced channels between the communicating parties to give us placed channels. Then we have party supermaps corresponding to local actions of communicating parties. Now, there's a minimal condition that any such resource theory must satisfy, namely no side channel generation, we have shown that the switch placement does not generate side channels. The superposition placement neither generates side channels, but note that these act on different input resources, so we still need to be careful when we compare them. And finally, superpositions of encoding operations do in general generate side channels, so should not be considered valid models of communication. Now, finally, we hope that this general framework can be used in the future to quantify differences, quantify the formalisms of any novel models of communication, including ones that are not directly related to the above examples. So to conclude, some ideas on future work would be to investigate really the second open question I posed at the beginning, the extent to which indefinite causal order per se gives advantages when compared to other protocols. But notably, this really needs to be restricted to the case where we only consider non-side channel generating operations and operations acting on the same initial resources. And finally, this framework could be extended to correlated quantum channels, so where the initial resources are actually can be correlated uses of the same device, which has also been shown to yield some interesting communication advantages. For example, in our new archive preprint you can see at the bottom. So with this, I would like to conclude my talk, and thank you very much for your attention.
All right, thank you so much for the talk. I see there's a few questions in Slack, so maybe I can start by the first one from Tomasz Gonda. So he actually asked two questions. Maybe I can start from the first one. So the question is the following. It seems to me that the structure of placement supermaps is what gets you from a theory of parallel composable channels, the standard SNC, to a theory of universally combinable channels, as per the paper by Bob, Tobias, and Rob. Is that a fair assessment?
Okay, thanks for the question. So I think that's one way to look at it. We haven't thought of it that way actually before, so that's an interesting point maybe for discussion later. What I will say on this point though is that in the current model, for example, we did not consider sort of indefinite causal structures, for example, in the quantum switch or superposition. We really considered the only parts that are placed are the kind of inputs and outputs. So we don't really consider what's happening in the middle. So in the middle, we haven't really understood how these things are being combined. We just say that there exists a mathematical operation that carries out this task. So for example, in a switch, in principle, if you look at this picture here, you should be able to see sort of at the bottom, I mean, there are these loops, and so there should be something in between N1 and N2 on one path, and similarly on the other path. But we haven't considered what's happening there. So maybe that's something that could be done in future work. But I take your point of the universally combinable processes. I would need to look into this further. Maybe we can discuss later.
All right. Let me maybe go to questions from other people and then go back to Tomasz, because there's, loads of questions. So Alex is asking, how does your no side channel generation condition for supermaps relate to the phenomenon of activation in quantum channels?
Okay, thanks for the question, Alex. So essentially, we're saying that the point of this, the point of the no side channel generation is that there are some activations of quantum channels which are completely trivial. So for example, everyone knows, from just standard quantum theory that if you have, let me see if I can find the example. If you have a C0 gate and if you have some message M and you have some noisy channels that you send through M, let's say completely depolarizing channels, then you cannot transmit information. But if instead I couple this message to a C0 gate, then which I initialize the control. Sorry, I couple it with the control through a C0 gate, and I initialize the control in the plus state. And simply by putting in the plus or minus states for a message, I can always get out one bit of information by measuring the control qubit. So this is kind of an activation, if you like. So it's some kind of way in which you have taken two channels and that are completely noisy and transformed them into a new channel that is not noisy. So But as the point really is that this kind of activation is really trivial. So it's stuff that we already know can happen, and it works for any channels, but doesn't depend on the original channels. So what we want to do with this condition is to really clarify what we mean by non-trivial activation. So for us, a non-trivial activation of communication capacity is when you have two completely noisy channels, for example, two completely depolarizing channels that on their own cannot transmit information, but you have some higher order map, so some supermap that takes those channels and maps it to a new channel which has non-zero capacity. But we need to enforce that this supermap does not work independently of what the initial resources are, because if that were the case, then the activation cannot really be said to be due to the channels if it works for every possible channel. Then but if it does not work for all channels, then there's a sense in which it's really, we can think of it as a way to use the channels in a new way.
All right, so there's lots of questions. I don't think we can actually go through all of them in the next 3 minutes that we've got left. I do have one of my own. Maybe I will put that forward first. Somehow here in this resource theory that you define, the enveloping theory, where you have the processes that you can apply in your channels, is basically composed of these supermaps. And then that's the thing that you partition into free and non-free. Do you think that this is like the most general thing that you can do, or are you losing some generality by restricting yourself to operations on channels that are written down as supermaps, or that corresponds to supermaps? What's your view on that?
So I mean, okay, so let's go back to
this is like maybe a question more towards the QPL audience that are more on the physics side rather than the math side.
Yes. So sorry. Can you, sorry, just to clarify the question? Do you mean, is there a more general thing that we can do with channels?
Yeah, that maybe it's not. What's your, like? Do you know if there's anything that is more general than super channels, and that whether having as the enveloping theory of your resource theory as these super maps would be a restriction on the kind of things that you can do, or if it's somehow there's
I see. Yeah.
this general thing. Mm-hmm.
Yeah, I mean, I think the way we are thinking of it is that supermaps are kind of are defined as the as transformations that map quantum channels to quantum channels in a well-defined way. So, for example, if you extend your channels to some other ancillary system, then the transformation on a part of a channel, supermap acting on part of a quantum channel, still gives you a quantum channel, and those sorts of things. So I guess if you allowed for other kinds of transformations of channels, then they wouldn't necessarily be well defined within the framework, because they would transform quantum channels to some other types of channels. But on that note, I would like to point out that this formulation I gave today in the 20-minute talk is a big simplification of the actual formalism of supermaps themselves. So there are, in fact, if you look at the mathematical structure of the placed channels and the unplaced channels, they have quite a lot of subtlety. So the unplaced channels can actually be thought of as no signaling channels. And then the placed channels can be thought of as quantum combs, or no signaling channels, or ordinary channels, depending on how they've been placed. And so there are some, in our paper, you can find really the actually mathematical conditions for each type of of placement supermaps and of party supermaps, and also of actually supermaps that act on the unplaced channels themselves. And we've come up with kind of admissibility conditions that tell you what possible types of supermaps should be allowed, depending on what they're acting on.
All right, so we're almost running out of time, so I think that we should thank the speaker again and move on to the next talk, which...
Yes. Thank you very much.
Mm-hmm. There's loads of questions in Slack, so go for them.
Yep, I will start answering them now. Thank you very much.